Welcome. Today we'll derive the expression for the magnetic field at a point on the axis of a circular current loop using the bios of our law. Let's start by drawing our setup. We have a circular loop of radius r carrying a steady current I. We want to find the magnetic field at point P, which lies on the axis of the loop at a distance x from the center. Let's recall the bios of our law. It states that the magnetic field dB due to a current element I dl at a point in space is given by this equation. Let's consider a small current element dl on our loop. The vector r points from this element to point P, and its magnitude is given by the square root of r squared plus x squared. Due to the symmetry of our setup, the horizontal components of the magnetic field from opposite elements cancel out. Only the vertical components contribute to the net field. The vertical component of dB is given by dB times cosine theta, where theta is the angle between r and the axis. Cosine theta equals x divided by r. Putting all this together, we can integrate over the entire loop to get our final expression for the magnetic field. This expression shows us that the magnetic field is strongest at the center of the loop where x equals 0 and decreases as we move away from the loop along its axis. Welcome to Math GPT. Today, we'll derive the expression for the magnetic field inside a long current carrying solenoid using Ampere's circuital law. Let's start by visualizing a solenoid. A solenoid is a coil of wire wound into a helix carrying a current I. For our derivation, we'll assume the solenoid is very long, has n turns per unit length, and is air-cored. To find the magnetic field, we'll use Ampere's circuital law, which states that the line integral of B dl around any closed loop equals mu naught times the enclosed current. Let's choose our Amperian loop carefully. We'll use a rectangular loop with one side inside the solenoid parallel to its axis, one side outside, and two perpendicular sides connecting them. Inside the solenoid, the magnetic field lines are parallel to the axis. Outside, the field is negligible, and along the perpendicular sections, B is perpendicular to dl. Let's evaluate the line integral. Only the path inside the solenoid contributes, giving us B times L, where L is the length of our path. Now for the enclosed current. With n turns per unit length, our path of length L encloses n times L turns. Each turn carries current I, so the total enclosed current is n Li. Putting this all together in Ampere's law, B times L equals mu naught times n Li. The L's cancel, giving us our final result. The magnetic field B equals mu naught Ni. This elegant result shows that the magnetic field inside a solenoid is uniform and directly proportional to both the current and the number of turns per unit length. Today we'll derive the expression for the force between two parallel current-carrying conductors and use this to define the ampere. Let's start by considering two long parallel conductors separated by a distance d. The first conductor carries current I flowing upward, and the second conductor carries current I2 also flowing upward. When currents flow in the same direction, the conductors experience an attractive force. Let's first find the magnetic field be created by the first conductor. According to Ampere's law, the magnetic field at a distance d from a long straight conductor is given by B equals mu naught I divided by 2 pi d. The magnetic field forms circular loops around the conductor, following the right-hand rule. At the location of the second conductor, the magnetic field points into the screen. Now, when the second conductor carrying current I2 is placed in this magnetic field, it experiences a force given by the Lorentz force law. The force per unit length equals I2 times B. Substituting our expression for B, we get the force per unit length equals mu naught I2 divided by 2 pi d. This expression forms the basis for the definition of the ampere. 1 ampere is defined as the constant current, which, if maintained in two straight parallel conductors of infinite length placed 1 meter apart in vacuum, would produce between these conductors a force of 2 times 10 to the minus 7 newtons per meter of length. Let's verify this definition using our equation. If we plug in 1 ampere for both currents and 1 meter for the distance, we get exactly 2 times 10 to the minus 7 newtons per meter, confirming our definition of the ampere. And there you have it. We've derived the expression for the force between parallel current-carrying conductors and seen how this fundamental relationship is used to define one of the most important units in electricity, the ampere. Welcome. Today we'll learn about the moving coil galvanometer, an instrument used to detect and measure small electric currents. Let's start by looking at the main components of a moving coil galvanometer. The device consists of a rectangular coil of fine wire that can rotate freely between the poles of a permanent horseshoe magnet. A soft iron cylindrical core is placed within the coil. This helps to concentrate the magnetic field and make it more uniform. The coil is suspended using phosphor-bronze hairsprings. These springs serve two important purposes. First, they conduct current to and from the coil, and second, they provide a restoring torque when the coil rotates. A lightweight aluminum pointer is attached to the coil. As the coil rotates, this pointer moves across a calibrated scale, allowing us to measure the current. Now, let's understand how it works. When a current flows through the coil, it creates its own magnetic field. This field interacts with the permanent magnet's field, causing the coil to rotate. According to Fleming's left-hand rule, the direction of rotation depends on the direction of current flow. The stronger the current, the greater the rotation, up to the limits of the spring's restoring force. The deflection angle theta is directly proportional to the current I flowing through the coil. This relationship can be expressed as theta equals K, where K is the galvanometer constant. In conclusion, the moving coil galvanometer is a precise instrument that uses the interaction between magnetic fields to measure electric current. Its sensitivity and accuracy make it an essential tool in electrical measurements and calibration. Welcome. Today we'll solve a problem about an electron beam passing through electric and magnetic fields. Let's start by understanding what we're given. Let's visualize the initial setup. We have an electron beam passing through a region where both electric and magnetic fields are present. The electric field points upward and the magnetic field points into the page. These fields create forces on the moving electrons. For part 1, we need to find the speed of the electrons when the beam remains undeviated. This happens when the electric and magnetic forces are equal and opposite. Let's write out our force equations. When we substitute the forces, we get QE equals QVB. The charge Q cancels out, and we can solve for velocity. V equals E divided by B. Plugging in our values, 3.4 times 10 to the 4th divided by 2 times 10 to the minus 3. This gives us a velocity of 1.7 times 10 to the 7th meters per second. Now for part 2, let's see what happens when we remove the electric field. Without the electric field, the electrons move in a circular path due to the magnetic force. To find the radius, we use the fact that the magnetic force provides the centripetal force needed for circular motion. The magnetic force equals the centripetal force, QVB equals mv squared over r. Solving for r, we get r equals mv over qb. When we plug in all our values, including the velocity we found earlier, we get a radius of 4.8 times 10 to the minus 2 meters. So to summarize, first we found the electron velocity when the beam was undeviated, and then we used that velocity to find the radius of the circular path when only the magnetic field was present. Welcome. Today we'll solve a problem about magnetic fields created by a circular current-carrying wire. Let's understand the problem step by step. We have a straight wire that is bent into a circular shape. A current of 1 ampere flows through this wire. We need to find the magnetic field at 2 points. Point O at the center of the circle, and point P which lies on the axis at a distance of 3 times the radius from the center. Let's first calculate the magnetic field at the center O. The formula for magnetic field at the center of a circular current loop is B equals mu0 I divided by 2R, where mu0 is the permeability of free space, I is the current, and R is the radius. Substituting mu0 as 4 pi times 10 to the minus 7 Tesla meters per ampere, and current as 1 ampere, we get 2 pi times 10 to the minus 7 divided by our Tesla. Now for point P, which is at a distance of 3 R from the center, the magnetic field at an axial point is given by B equals mu0 I, r squared divided by 2 times the quantity r squared plus x squared to the 3/2 power, where x is the distance from the center. Substituting x equals 3r and our values for mu0 and current, we get 2 pi times 10 to the minus 7 r squared divided by 10 r cubed. After calculating these expressions, we find that the magnetic field at the center, O, is 2.5 times 10 to the minus 6 Tesla, and at point P it is 0.0079 times 10 to the minus 5 Tesla. Notice how the magnetic field is stronger at the center and weaker as we move along the axis, which is shown by these magnetic field lines. To summarize, we use the appropriate formulas for magnetic field at the center and on the axis of a circular current loop, taking into account the current of 1 ampere and the geometric relationships. The magnetic field decreases as we move away from the center along the axis, which is a key characteristic of magnetic fields from current loops. Welcome. Today we'll solve a problem involving magnetic fields created by 2 concentric circular coils. We have 2 coils with different radii and number of turns arranged at right angles to each other. Let's find the resultant magnetic field at their common center. Let's visualize our setup. Here's our first coil with radius 0.1 meters and 5 turns. And here's our second coil with radius 0.05 meters and 10 turns, arranged perpendicular to the first coil. A current of 2 amperes flows through each coil. To find the resultant magnetic field, we'll first calculate the field due to each coil separately. The magnetic field at the center of a circular coil is given by B equals mu naught Ni over 2R, where mu naught is the permeability of free space, N is the number of turns, I is the current, and R is the radius. Let's calculate B1 for the first coil. Plugging in our values, mu naught is 4 pi times 10 to the minus 7, and 1 is 5 turns, I is 2 amperes, and our 1 is 0.1 meters. This gives us 2 pi times 10 to the minus 5 Tesla. Now for the second coil. We use the same formula, but with N2 equals 10 turns, and our 2 equals 0.05 meters. This gives us 8 pi times 10 to the minus 5 Tesla. Since the coils are perpendicular, their magnetic fields are also perpendicular. We can find the resultant field using the Pythagorean theorem. B equals the square root of B1 squared plus B2 squared. Plugging in our values and calculating, we get 25.89 times 10 to the minus 5 Tesla. And there we have it. The resultant magnetic field at the common center of our 2 perpendicular coils is 25.89 times 10 to the minus 5 Tesla. Thanks for watching. Welcome. Today we'll solve a problem involving the magnetic force between parallel current-carrying conductors. Let's look at our problem. We have 2 parallel conductors, each 2 meters long, separated by a distance of 0.2 meters. Each conductor carries a current of 3 amperes. We need to find the force between them and the force per unit length. Let's visualize this setup. Here are our 2 parallel conductors. Current flows in the first conductor from left to right, and in the second conductor also from left to right. The distance between them is 0.2 meters, and each conductor is 2 meters long. When current flows through a conductor, it creates a magnetic field around it. The magnetic field lines around the first conductor form concentric circles. Similarly, the second conductor creates its own magnetic field. These magnetic fields interact with each other, creating attractive forces between the conductors since the currents are flowing in the same direction. The force per unit length between parallel conductors is given by this formula. F equals mu naught times I1 times I2 divided by 2 pi times d, where mu naught is the permeability of free space, equal to 4 pi times 10 to the minus 7 Tesla meters per ampere. Let's substitute our values into the formula. We have 4 pi times 10 to the minus 7 times 3 amperes divided by 2 pi times 0.2 meters. After simplifying, we get 9 times 10 to the minus 6 newtons per meter. To find the total force, we multiply the force per unit length by the length of the conductors. 2 meters times 9 times 10 to the minus 6 newtons per meter equals 18 times 10 to the minus 6 newtons. So our final results are: the force per unit length is 9 times 10 to the minus 6 newtons per meter, and the total force is 18 times 10 to the minus 6 newtons. The forces are attractive because the currents flow in the same direction. Welcome to this physics problem, where we'll calculate the net force on a rectangular coil placed parallel to a current-carrying conductor. Let's first understand the setup. we have a long straight conductor carrying a current of 20 amperes. Parallel to this conductor, we have a rectangular coil with length 0.25 meters and breadth 0.1 meters, carrying a current of 12 amperes. The distance between the conductor and the closer side of the coil is 0.02 meters. To find the net force on the coil, we need to consider the magnetic field created by the conductor. The magnetic field lines form concentric circles around the conductor, and their strength decreases with distance. The magnetic field B at a distance d from a long straight conductor is given by B equals mu0 times I over 2 pi d. The force on each side of the coil can be calculated using F equals ILB, where I is the current in the coil, L is the length of that side, and B is the magnetic field at that location. Since the magnetic field strength is different at the two parallel sides of the coil, they will experience different forces. Let's calculate the forces. For the closer side at 0.02 meters, the force F1 equals 12 amperes times 0.1 meters times the magnetic field at this distance. For the farther side at 0.27 meters, F2 equals 12 amperes times 0.1 meters times the magnetic field at this larger distance. The net force is the difference between these forces. After plugging in all values and calculating, we get a net force of approximately 5 times 10 to the negative 4 newtons, acting towards the conductor. This force arises because the magnetic field is stronger on the side closer to the conductor, resulting in a net force towards the conductor. Welcome! Today we'll learn how to convert a galvanometer into an ammeter and voltmeter. We have a galvanometer with a resistance of 50 ohms that requires 2 milliamps for full-scale deflection. We need to convert it into an ammeter with range 0 to 3 amps and a voltmeter with range 0 to 5 volts. Let's start with converting the galvanometer to an ammeter. Here's our galvanometer. To convert it to an ammeter, we need to add a shunt resistor in parallel. The shunt resistor allows most of the current to bypass the galvanometer, protecting it from high currents. To calculate the required shunt resistance, we use this formula. S equals Ig times Rg divided by Ia minus Ig, where S is the shunt resistance, Ig is the galvanometer current, Rg is the galvanometer resistance, and Ia is the desired ammeter current. Let's plug in our values. We have 2 milliamps times 50 ohms divided by 3 amps minus 2 milliamps. This gives us approximately 0.03335 ohms. Now let's convert our galvanometer to a voltmeter. For this, we need to add a series resistor. The series resistor limits the current through the galvanometer based on the voltage being measured. The formula for calculating the series resistance is R equals V divided by Ig minus Rg, where R is the series resistance, V is the desired voltage range, Ig is the galvanometer current, and Rg is the galvanometer resistance. Let's plug in our values. 5 volts divided by 2 milliamps minus 50 ohms. This gives us 2,450 ohms. In summary, to convert our galvanometer, for an ammeter, we need a shunt resistor of 0.03335 ohms. For a voltmeter, we need a series resistor of 2,450 ohms.